Hello everyone. So, this is the third week of this course, and yeah, we will be starting with the optimization algorithms. You can recall that we had the introduction session in the first 2 weeks. In the first week we introduced how to solve an optimization problem analytically, and we spoke about constrained and unconstrained optimization problems, existence and uniqueness of a solution, convex sets, convex functions, and then about the first order conditions, second order conditions, and so on. In the second week we learnt Python coding in detail, right. So, yeah, those were you can say that they are a kind of introduction to the course, and from this week onwards, the third week, we will actually go into the optimization algorithms, which was the topic of this course in the first place, right. So, recall that we had two broad classification of optimization problems, the unconstrained and constrained optimization problems, right. So, if you consider an unconstrained optimization problem, so we first consider a function f Rn to R, which is twice differentiable, and if you recall how an unconstrained problem looks like, you have to minimize f of x subject to the condition that x can take any value in Rn, right. So, this is the very basic problem, and we actually know how to solve an unconstrained problem analytically, right. So, the first question that should come to our mind is, why do we need optimization algorithms in the first place? Why not continue solving them analytically when we know them, when we know how to solve a given problem analytically, right. So, there are two basic reasons. Okay. So, the first reason is, so yeah, I will just write it as reason 1 for example. Okay. So, yeah, the first reason is that not all problems can be solved analytically. Okay. So, yeah, it is so we use the term analytically intractable. So, I will give you a few examples. So, let us consider a function that goes from real line to real line. Okay. So, and let us define the function as x minus 1 into e power x minus x. Okay. So, yeah, this is a nice function, you can actually draw this draw the curve very easily, right. And so, if I had given you to given this problem to you to solve analytically, you will differentiate this and equate it to 0. So, what is the derivative of this? So, you differentiate x minus 1 into e power x. So, that is so if you keep this constant, then you get x minus 1 into e power x, and yeah, when you keep this constant, then you just get e power x, and you get minus 1 equal to 0. So, you have x e power x equal to 1, right. So, what is the solution for x e power x equal to 1? Not known, right. I mean, it cannot be analytically solved. So, I mean, some of you who might have seen something called as Lambert W function might know that this is actually the Lambert W of 1. Okay. Yeah, but those are not usual functions that we are aware of, right. So, yeah, so this problem cannot be solved analytically. So, you cannot give me an x for which x e power x is equal to 1, right. In a similar way, I can give you another example which again goes from R to R, and now the function is x squared plus e power x. Okay. So, in this case you can see that f dash of x is 2x plus e power x, which needs to be 0, and this again cannot be solved analytically, right. So, note that these are all functions from going from real line to real line, right. So, these are not even multivariate functions, these are actually univariate functions, f depends only upon one variable, right. Imagine if I give such problems in 2 dimensions or 3 dimensions, right. So, I mean just for an example, let us say I give you a function f that goes from R2 to R, where f of x1 comma x2 is x1 e power x2 plus x2 e power x1, right. So, if you solve this analytically, you have to look at the following I mean you will have to solve the following equation simultaneously. So, which is e power x2 plus x2 e power x1 equal to 0 and e power x1 plus x1 e power x2 equal to 0. Okay. We knew that it was difficult solving even one of these equations, right. So, how would you solve 2 of these equations simultaneously, right. These cannot be solved analytically. So, these problems are in mathematical parlance called as analytically intractable. So, they can be tracted using some other methods, for example computationally, right, but analytically they cannot be tracted, right. So, that is why we are calling them as analytically intractable problems. So, in practice we have a lot of problems of this sort where the problems are not analytically tractable, right. So, that is one main reason why we actually go for optimization algorithms and I mean not just stop with solving them analytically, right. There is another important reason which is more suited for today's scenario, right. So, I will write down reason 2. So, even if the problems are analytically tractable, the problems could be large. For example, the dimension of the optimizing variable or the number of constraints are large. Okay. So, what do you do when you, so I mean whatever problems we are solving analytically, we know that we can solve them analytically, but whenever we take examples, we take examples of 2 dimensional problems or 3 dimensional problems or 4 dimensional problems. Do we ever take an example of a 10 dimensional problem and try to solve them analytically? That never happens, right. But if you see the problems that we have at hand in today's scenario, specifically after the advent of machine learning, right, we have problems where there are hundreds of features, right. So, the starting problem comes to us, the dimension of that problem is 100 is equal to 100 or maybe much more than 100, right, and the number of constraints that you have is also huge, right. So, and when we actually go to big data, right, so the number of data points are actually huge, right. So, I mean solving them analytically is out of question. We actually want to give to the computer all the optimization problems that we have at hand, right. So, that is exactly what we are trying to do, okay. And I will actually give you an example of a practical scenario where you actually have the number of optimizing variables to be large or the number of constraints to be large. This is an example that we have seen in the very first lecture for I mean I call that support vector machine, I do not know if you remember, okay. The problem is as follows: you minimize half norm w squared with respect to w and b subject to the condition that yi into w transpose xi plus b is greater than or equal to 1 for I equal to 1 to n. right. So, yeah, I mean if you do not recall the setup, you actually have n data points like what you have in a machine learning scenario, right. So, you have x 1 y 1 x 2 y 2 dot 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 x n y n, right. So, yeah, y I belongs only to minus 1 or plus 1, but x I is any real number in R n, I should say R p maybe. Okay. So, you can actually see that the dimension of W is p, which is usually in the order of tens or even hundreds based on the problem, and B is one dimensional. So, we have, so let us say P is 10 and N is say 1000. Okay. So, we have a data which is you have 1000 data points and each data point is of 10 dimensions. Okay. So, then the dimension of the optimizing variable here is 11, okay, and the number of constraints, if you look at what you have here, this is a constraint for each I. For each data point you have a constraint. So, that means if you have 1000 data points, you have 1000 constraints. Okay. So, imagine solving a problem of this scale having 11 optimizing variables and 1000 constraints. This is the problem that we are actually staring at I mean in current day scenario, right. So, that is the reason we actually want to outsource all of these work to a computer, because solving it by pen and paper is simply impossible, right. So, that is I mean these are two very basic reasons why we are actually moving to algorithmic framework for optimization problems, leaving out the mathematical or analytical framework as we usually put it. Okay. All right. So, I think this is a sufficient motivation. We will now try to understand how to actually construct an algorithm, right. So, let me actually start with a very simple example. Okay. So, let us say f is a function from R2 to R and f of x1 x2 is equal to x1 squared plus x2 squared. So, yeah, very simple problem, because I mean just by seeing this you will tell me that minimizing this the minimizer of this function happens at x1 x2 equal to 0 comma 0, right. Yeah, I understand that. So, but I am trying to explain the algorithm with a simple example in mind, so that you understand how the algorithm actually works. Okay. So, if you want me to draw this function, so it is in 3 dimensions. So, this is x1 and x2 and x3, imagine that it is actually above this, coming above this. So, it will be like an open bowl, right. Yeah. So, this is like an open bowl facing upwards, okay, and of course, the minimum occurs when x1 x2 equal to 0 comma 0, okay. But for the moment let us assume that we do not know where the minimum is, okay. So, how do we actually frame an algorithm to find that the minimum occurs at 0 comma 0, right. So, let us actually take an arbitrary point, okay, say x0, x1 0 and x2 0, okay. So, start with an arbitrary point okay. So, I am starting at some point. I first need to figure out a particular direction in which I have to go, right. So, what is x1 x2 I mean x1 0 x2 0, right. So, it is like, so since we are in 2 dimensions, okay, x1 0 x2 0 is like just a point in this plane x1 x2, right. And from here I can actually move in any direction, right. So, I have just 360 degrees. So, I can move, for example, I can move like this way, this way, this way, this way, this way, this way, yeah, any I mean I can move in any of these directions, right. So, the I am actually at a loss to know when I start at a particular point I do not know which direction to move, right. So, the first way to think about which direction to move is if I move in that particular direction, okay, the first thing that I want to have that I want to see is that the function value decreases, right. In other words, let us say I choose a direction d for a direction d. So, d is d1 comma d2 in this example, okay. We need f of x naught plus alpha d is less than f of x naught for sufficiently small alpha positive, okay. So, to give an example, okay. So, let us say this direction x naught is actually 5 comma sorry this initial the arbitrary point x naught is actually 5 comma 4, okay. So, that is the point, and I can choose any direction in 360 degrees. So, it can be 1 0 0 1 1 1 1 minus 1 minus 1 minus 1, anything is possible, right. So, let us say for example, I choose d equal to minus 1 comma 1, okay. I am just giving some arbitrary values to explain what this f of x naught plus alpha d less than f of x 0 means, okay. So, yeah, when do I call this the right direction, right. So, find f of x naught is x naught 1 I mean x 1 naught squared plus x 2 naught squared, right. So, that is 5 squared plus 4 squared, which is 41, okay. Now, if I move from 5 comma 4 in the direction of minus 1 comma 1, okay, my function value must decrease, right. Yeah, it may not happen for all possible alpha, that is if I keep moving it does not mean that the function value needs to decrease always, but at least for some small values of alpha positive the decrease must happen. If that happens, then I am possibly in the right direction. I mean I do not want to increase the function value because I want to minimize f, right. So, I do not want to increase the function value, right. So, for example, let us take alpha is equal to half, I mean since we are asking for sufficiently small alpha, right. So, let alpha equal to half. So, f of x naught plus alpha d, so d is minus 1 comma 1. So, you have 5 minus half the whole squared plus 4 plus half the whole squared. So, this is 4.5 the whole squared, which is 20.25, and this is again 4.5 the whole squared, which is again 20.25, which is 41.5 sorry 40.5, which is less than 41, right. So, I started at a point 5 comma 4 and I just chose an arbitrary direction which is minus 1 comma 1, and you can see that this particular direction satisfies the property of this f of x naught plus alpha d less than f of x naught, at least for sufficiently small alpha positive, right. So, such a direction which satisfies this property, okay, is called a descent direction. that is the function value decreases when you move from x naught to x naught along this direction d. Okay. So, my first objective, so note that I have started here with an arbitrary point x naught. Okay. So, my first task is actually to find a descent direction for f at x naught. Okay. Fine. So, how do I find it? Yeah, so I have this equation which says f of x naught plus alpha d is less than f of x naught, I agree with that, but I want to I mean given an x naught and given an f, can I immediately come up with a d? That is the question that we have with us, right. It is actually easy. So, let us actually use the Taylor's expansion of f of x naught plus alpha d. Okay. So, you know that it is f of x naught plus alpha d transpose del f of x naught. Okay. So, what we wanted was f of x, so we want this to be less than f of x naught, and we also know that alpha is positive, right. So, what we are looking for is changing this has I mean no effect. So, I have just written d transpose del f of x naught as del f of x naught transpose d, right. So, the dot product of these two vectors should be less than 0. So, if you give me an f and if you give me an x naught, I can find the value of d for which the gradient of f at x naught has the dot product with d to be negative. The dot product of the direction with the gradient of f at x naught is negative. If that happens, then such a direction is actually called as the descent direction, right. Yeah, so this is actually approximately equal to, right. So, yeah, now if you take this particular example where f is x1 plus x1 squared plus x2 squared and x naught is 5 comma 4. Okay. So, what are all the directions that can be called as the descent directions, right. So, we know that del f of x naught is 2 x1 0 2 x2 0, which is 10 comma 8, right. So, any d that satisfies 10 d1 plus 8 d2 less than 0, right, is a descent direction. Okay. So, yeah, if you want to draw how it looks like the following. So, we want 10 d1 plus 8 d2. So, let me put 1 2 3 4 1 2 3 4. So, this is minus 4, this is 4, 1 2 3 4 5, 1 2 3 4 5, right. So, you can substitute minus 4 comma 5, right. So, that comes out to be 0. So, plot that particular point, of course, you will have 0 comma 0 and you will also you can also have 4 and minus 5. So, it is here. So, join these lines and this is actually 10 d1 plus 8 d2 equal to 0, right. So, less than 0 is all of these directions. Okay. So, you can choose any directions in this shaded region, of course, not the line, because there it is equal to 0. So, anything to the left of that line. Okay. So, for example, so I have so here you can see that I have chosen minus 1 comma 1. You can see that minus 1 comma 1 yeah, actually lies slightly to the left of this line, right. So, of course, you can choose any other point as well. You can choose minus 4 comma minus 4, minus 4 comma minus 5, minus 100 comma minus 92, all of these will lie to the left of this line, right. So, any direction in the shaded region what I have written here is the descent direction of f at x naught, at the point x naught. Okay. All right. So, yeah, I think we have learnt very clearly what a descent direction is. Okay. Now, we should actually understand what is the value of alpha. Okay. So, fine, yeah, I mean we got to understand how to choose D, and we need to choose one of the descent directions. Okay. So, we first started with an arbitrary point. Okay. And the second step is actually, so after starting with an arbitrary point, start with an arbitrary point, x naught x1 0 x2 0, and then choose a descent direction D such that del f of x naught transpose D is less than 0. Okay. We still, so yeah, so I told you that descent direction satisfies this property, right. Sorry, it should be less than, yeah. So, but that does not happen for all possible alpha, right. So, I just mentioned it is sufficiently small alpha positive, is not it. So, what does that sufficiently small alpha means? That means it may not work for all alpha positive, it works only for certain alpha positive, and you want to figure out for which alpha I mean this condition holds, right. So, we will do that. So, let us consider the same example, right. So, let us say f is x1 squared plus x2 squared, x naught is 5 comma 4 and D is minus 1 comma 1. So, let us find the values of alpha for which this equation holds, right. So, f of x naught plus alpha D minus f of x naught, okay, is 5 minus alpha, right. So, x naught 1 is 5 and D 1 is minus 1. So, x 5 minus alpha the whole squared plus 4 plus alpha the whole squared minus 41. So, f of x naught is 5 squared plus 4 squared which is 41, right. So, you have minus 10 alpha plus alpha squared plus 8 alpha plus alpha squared which is yeah minus 2 alpha plus alpha squared. Okay. So, yeah I can also write this as alpha into alpha minus 2. So, this is less than 0 only when oh I am sorry, this is 2 minus 2 alpha plus 2 alpha squared, sorry. Okay. So, this becomes 2 alpha into alpha minus 1, yeah, less than 0 only if alpha in 0 comma 1, right. So, we know that alpha is greater than 0. So, but we have to choose an alpha that is strictly less than 1. Okay. So, what this tells us is it does not suffice to just choose a descent direction, we also need to choose something called as a step size, okay, alpha. So, choose a step size alpha such that f of x naught plus alpha D is less than f of x naught. Okay. So, yeah we first started with an arbitrary point, then we chose a descent direction and then we chose a step size and we then write x1 is equal to x naught plus alpha D. Okay. So, I will actually write this as D 0 and alpha 0, so that is the reason why I do this. Okay. Yeah. So, then I have to, yeah, fine. So, this is the next point. So, we started with an arbitrary point x 0. So, we reached another point x 1, but this is not the final answer, right. So, but what do we do next? very simple, repeat this procedure, right. So, you now choose d1 such that del f of x1 transpose d1 less than 0 and alpha 1 such that f of x1 plus alpha 1 d1 is less than f of x1, okay. And then it becomes x2 equals x1 plus alpha 1 d1, okay, and you keep continuing. Now, the question is when to stop, right. So, when do I know that I have reached the right answer. So, for this example the answer is easy because you know the answer 0 comma 0, but when you do not know the answer, how do I come to the conclusion that we have actually reached reached close enough to the right answer, right. So, yeah, so what you actually do is, so you know that at the critical point the gradient is actually equal to 0, right. So, you stop when del f of x k is close enough to 0, or speaking practically we usually choose a tolerance, okay, say about 10 power minus 6, 10 power minus 8, or you can choose a lower tolerance if you want, okay. So, when del f of x k is close enough to 0, okay, at that point we actually stop, okay. So, the algorithm is actually I mean putting all of this together, okay. So, I will write down the following algorithm. So, first initialize x naught, right. So, you first need to start with a point. So, choose that point basically, okay, and now you need to start a loop while del f of x k, yeah, you have to also initialize the tolerance value. Del f of x k is greater than the tolerance, okay. Yeah, you can initialize k equal to 0 as well. Until this, what all you do, you first choose dk such that del f of x k transpose dk less than 0, and so this is choosing the descent direction, okay. And the next step you actually choose the alpha k such that f of x k plus alpha k dk is less than f of x k, then you write x k plus 1 is x k plus alpha k dk, and then write k equal to k plus 1, okay. The output is x star equal to x k, okay. So, when you come out of del f of x k when it is less than or equal to tolerance, you actually come out of the while loop and you actually print this, okay. So, yeah, so this is a formal algorithm what I have defined, okay. I will actually spend 2 minutes explaining what all these actually means, right. So, this is actually something what you do practically, okay. So, let us say you are actually starting from some village, okay. So, you want to go to a village which is like 100 kilometers away, okay. So, but you do not know anything, I mean you do not have any directions anything. So, what do? You actually ask someone. So, I want to go to this village, so what do I do, right. So, what does that person tell you? So, since it is not very nearby, let us say it is about 100 kilometers away, right. So, he actually first says go in this particular direction for certain number of kilometers, right. So, go in this particular direction for maybe 1.7 kilometers, right, for example. So, fine, you go there, you have not reached the destination. What do you do then? You ask someone else, what I mean how do I reach that village, right. So, he says okay, go in this particular direction for 2 kilometers, right. You go there, you have not reached the destination as yet, you ask someone else, right. So, he again tells you okay, travel in this direction for so many kilometers, this keeps on going, okay, but when do you stop? The last person, when you are very near to the destination, right, he actually tells you okay, go in this direction for maybe 100 meters, okay, you will actually see a board saying that that is your destination, right, there you can stop. So, what does the last person tell you? The last person does not just tell you the direction and the step size, he also tells you the stopping criterion. Okay. So, that is exactly what we have done here. At each step you are actually told a particular direction and the step size, okay. That happens for many iterations, right, and at the final step you are also told you can stop there. So, you are able to see a board where del f of x k is less than or equal to the tolerance, right, what I have written here. So, when you see the board you go there and stop. Okay. So, that is the basis of any optimization algorithm that we are going to see throughout this course. Let us see in the next lecture. Thank you.